Hello students, in this video we'll discuss the transformation law for covariant components of a contravariant vector. So let's be given, this is the starting point for all these calculations, a covariant basis, E1, E2, E3. We can form a dual basis, or as we know for R3, it's called a reciprocal basis. E1 upper, E2 upper, and E3 upper. Okay, and of course we know what that is for R3, right? All right, and so what I want to do is I want to consider a different set of coordinates, a different set of covariant coordinates, right? Also, given, we've seen how to do this in a previous video, another covariant set, basis, E1 tilde, E2 tilde, E3 tilde, and of course we can see that the notation starts to get clumsy here, right? So that's something we have to embrace, the fact that the notation gets a little bit hectic as we go about this business of extending these to higher dimensions into higher order tensors, okay? Then we have some transformation laws, right? Then we know that EI in this first covariant basis is going to be equal to what? It's going to be equal to Pij for some matrix Pij, and then E tilde j. And I know that conversely, and I know that E tilde I is equal to Qij. In the previous video, we saw that these matrices Pij and Qij are inverses of each other, right? And we know, of course, how the components transform, right? And we know, therefore, that if I look at V also, we have a previous result, our previous proposition, is that if a vector V is really Vi and then Eij, like that, then this implies that Vi is going to transform like what? It's going to transform like the Q's, or Vi tilde is going to transform like the P's, right? So this is going to be a Pji like that, and then the I goes on the upstairs, so I'm going to have a Vj like that. In other words, the components, these contravariant components of this covariant basis transform the opposite way that the vectors themselves transform, right? Now I want to do the same thing for the flipped for this contravariant basis, right? So recall that in this dual basis, what do we have in this dual basis? So recall that this dual basis is characterized by the following fact that EI and then EJ upper is delta Ij, this Kronecker symbol over here. That's the Kronecker symbol. Okay, excellent. And so now what can I do? So now what I want to do is I want to find a rule. I can expand also these any vector in terms of this contravariant basis, right? So vector V is also equal to Vi lower now. So these are Vi lowers, like that. Vi lower, these are called the covariant components of a contravariant vector, and then EI upper like that. So these VI's, here the VI's are called the what? Those are called the covariant components of the vector. Okay. All right. And so now, of course, I can write my vector in either there's also a dual to this, the corresponding contravariant basis has another dual vector dual to it, right? And this thing has a dual of what? Of E tilde 1 upper, E tilde 2 upper, E tilde 3 upper, this contravariant basis, and it has the same sort of property over here that the tildes, the same relationship over here works for the tildes as well. Excellent. So now what I want to do is I want to find a transformation law for these covariant components. So let's do that. Okay, so let's look now, let's consider a vector V, which I can write how? A vector V can be written as Vi and then EI upper, and it can also be written as Vi tilde E tilde I upper, like that with the tilde coordinates, right? So I can write V in terms of this contravariant basis EI, or in terms of the contravariant basis EI tildes. Okay? Either of those are valid. And so now let's consider, how do I compute these coefficients over here? So these coefficients, a coefficient to Vi, for example, would be what? Would be let's say Vj, you could say Vj, and then delta I j like that. Okay? that would pluck out the I components, right? Now, delta ij is exactly equal to these what? Is exactly equal to these ei's, right? So this is exactly going to be what? This is exactly going to be vj, and then I'm going to have an ej. I can say ej dot ei, for example, like that, right? Okay. And I've just used the fact that delta ij is ei dot ej, right? And I can change the dot product as commutative over here. It doesn't matter what order I do them in, I just arrange it in the right way. All right, excellent. And so now this is going to be what? So now I'm going to transform these things into the same thing as vj tilde, and then e tilde j like that. Excellent. Dot a ei. And now how does ei transform? Ei transforms in the following way. So now the ei relationship is over here, right? That's going to be a pij, like that. And then what? And I should probably replace the j with a different dummy index over here. So I'll replace that j with a k. Okay, I'll replace that with a k. And then what? And then I'm going to have a what? And then an e tilde k. E tilde k over here, like that. Let's see, so then e tilde with the k in the lower, right? Okay, and here I'm using what? I'm using this transformation law over here, so everything goes on the lower now, right? And so now I have a reciprocal basis, so what is this over here? So this is going to be vj tilde, and then this is going to be a e tilde j, e tilde k, that's going to be a pik, and then a delta jk, kj over here. And of course, when I have a delta jk, I can replace all the k's with j's, so this is going to be a vj tilde, and then a pij like that. So I have a transformation law for these contravariant components. What's the transformation law for these contravariant components? The law is this, is vi is equal to, and again, flipping the way we do the multiplication to make it consistent with matrix multiplication, is pij, and then vj tilde like that, okay? And now notice what? Notice that the covariant components transform the same way as the covariant vectors do. So that's an important thing to note. So note the covariant components of the contravariant vector transform the same way as the what? As the covariant vectors. In other words, the covariant components transform the same way as the covariant vectors themselves. And analogously, we're going to see the contravariant components do the exact same thing. So we can run through the same calculation and see the same result is true for the contravariant components, right? So in other words, how are we going to compute these contravariant components over here? So let's do that next. And so similarly, what can we do? We can consider a vector, v, and the contravariant components, right? So in other words, I'm going to write this as vi lower, and then ei upper, and that's also equal to what? Is also equal to vi tilde, and then v what? Tilde I upper. And I'm going to change that dummy index to a j over here. So I'm going to write that as j, like that, and then an e tilde j upper, like so. Okay, excellent. And so now what can I do over here? So now I want to write down this transformation law over here for these contravariant things over here. So how do the contravariant vectors transform? The contravariant vectors transform I want to figure out how they do that, right? And so what we're going to do is we're going to write down this covariant transformation law over here. This is going to be what? So of course the vj's are going to be the qj's, right? So this is going to be a qj over here, like so. So this is going to be a qj. I'm going to replace these vj's over here by this transformation law with qij. So that's going to be a qij, qj, qji, and then a vi like that. And I'm going to turn that actually I into a k, so I can make this my life a little bit easier, but let's just see how we can make this work. So it's important to make have the indices work in the same direction, so let's actually change that momentarily just to a k, right? We can always change back later, right? And that will give me a vj tilde, right, according to this transformation law right over here. And that's going to be e tilde what? E tilde j like that, right? And now I can also write down this transformation law for I want to write down the transformation law for e tilde j, so I can replace all the j's with I, right? So in other words, I'm summing over j, so I can write this as q I k, and then v k, and then an e tilde, and I want to leave these as i's actually, so I want to replace the k's with I'll replace the k's with i's. So give me 1 second here. Replace the k's with i's. So we're gonna have that. The j's with i's actually. I want to make sure I'm getting this correct. I want all the vk's to be i's. Yeah, so this is going to be q I j v I, and then e tilde j like so. Okay, excellent. And so these things are equal to each other. That's equal to this, right? So playing around the dummy indices, as you can see from this calculation, it's important to understand how you play with the dummy indices to make it work out in the right way, right? It's never important. You never want to be able to look at your notes and say, where's the I, where's the j, where's the k? Just sort of sit down and figure out what you need to work in order to make sure that the indices are consistent, right? And so now what this tells me is that this expression over here is equal to this expression over here. Therefore, this tells me that vi times the quantity what? Times the quantity of ei upper minus qij, qji upper, and then e tilde j like that is the zero vector, like that, okay? So that's the zero vector for all choices of vectors, which means that these quantities over here have to be equal to each other. And therefore, we have a transformation law for the covariant vectors, the contravariant vectors themselves. Hence we get that e upper I, that's contravariant basis, is going to be what? It's going to be q j I upper, and then e tilde j upper like this. And so that's the transformation law for contravariant vectors. And the transformation law for contravariant vectors is exactly the same thing as the transformation law that we're going to get for the contravariant components that we saw from our previous video. So in other words, the contravariance transformation laws are consistent between contravariant components and contravariant vectors. The transformation laws are identical for covariant components and covariant vectors over here. We get the same exact structure over here, right? So in other words, this idea of covariance, all these covariant quantities share the same transformation law, and the contravariant quantities share the same transformation law. And so that gives us a way to sort of leverage the idea of like what a higher order tensor should be, which we're going to see in further videos. Now what we're going to do is we're going to consider inner products of these tensors of order 1. So in other words, a vector is in some sense a tensor of order 1 because it transforms in the right way, so to speak. And so now we're going to try to define what it means to be a tensor of order 2, and that goes back to this idea in calculus, in Calc 3 or in multivariable calculus, when your instructor said, well, we can do the dot product of vectors, we can do the cross product of vectors, but we can never, ever, ever multiply vectors. In fact, we can, and that's something called an outer product. And in further videos, we're going to see that these tensors of order 2 are really outer products of vectors, and in general, a tensor of order 2 has this sort of a decomposition in this fact, and we're going to highlight that decomposition in further videos. Thank you very much.